Hi, this is Aaron Holmberg at Corvallis Middle School, and this video is about understanding the long division standard algorithm. I'm going to be using several sort of versions of the algorithm, which more or less rely on pictures to help kids understand a couple things. First of all, what's most important here is to understand that this video is about teaching long division, the traditional way that people have been doing it. But I'm going to show some ways that reach up to that. So the biggest problem that I find in teaching kids the division algorithm, whether 4th or 5th grade here, is that they often don't know where the answer is going to be written, where their work is going to be recorded. When you do addition and subtraction and multiplication, you generally work from the top down and your answer is on the bottom. But in the division algorithm, you subtract down and your answer ends up being on top, recorded as a series of steps with place value. So this first page here, and this is just a page of notes that I have for my class, teaches the kids about how and where to count and what the repeated subtraction of division is doing. So I often have them just pick a divisor, a small number, a single digit like this or something, and then we practice at first just circling groups of that number because they are being subtracted away repeatedly, and we use tallies on top to keep track of the number of times we're subtracting those things away. So it's the idea of how many times does 4 go into this. It's actually how many times is 4 subtracted from this amount. And that's the same thing that's happening, of course, in the standard algorithm. So I'm going to go through and just circle all of the groups of 4 that I can find. Doesn't matter what shape I make of them as long as I know that they are groups of 4. And there, whoa, my pencil's broken. There I have 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6 groups, and I have a remainder here. I'll change color, and my remainder is just 3. So if I wanted to do kind of the 3rd or 4th grade way of saying it, I'd probably say 3 over here. But eventually what I do with students too is I quickly relate that this is 4, and we had 6 groups of 4. There's 24, and the 3 that are here means that there were 27. So that goes in there 6 times, and we would subtract 24 and 3, and that their answer should be 3/4, which is the fraction, their quotient answer like that. So I'm trying, by the way, to show that this is the same thing as this, but I often do several steps of it just in this way on this page. It says finding the quotient of a picture divisor using tallies. On the next page, I do something similar. And the point of this is to, again, show that the work is going to go down and the answer is going to be recorded on the top. So if the students pick a divisor, like say they pick 2 on this one, what we're doing is we're just subtracting 2's. So I would have them write down a -2 because I'm trying to develop the idea that you're going to be subtracting downward. And then they cross off, they mark it down, take away a 2, take away 2. Every time that they're taking away 2's here, in this case they take away all of them. But they just keep repeating this fact that they're taking away 2's, 1, 2, 3, 4, 5, 6, 7, 5, 6, 7, and that would get them down to 0. I'll move that up so you can see it. And of course they would have kept track of 1, 2, 3, 4, 5, 6, 7 2's being subtracted. And then I ask them, I say, what if this was the standard algorithm? Would that be good enough? And the students are like, no, because it gets really long, and if you had really large numbers of things, it would take you forever to do them. And so they start to realize that this would not make a good standard algorithm. The next page that I go to is kind of I won't bother to read the story to you on top, but we always relate it to stories. We take a number like this and say, okay, it's no longer a picture, it's 98, and we're taking 5 from it. And how would you go about doing that? Well, literally it means you're subtracting 5. And so you're at 93, and then you're at 88, and then you're at 83, and so forth. And pretty soon the same thing happens. Students are like, this is really silly. Why are we taking away all these 5s? Counting them up here, we could take a bunch away at once. We could take away 10, for example. And 10 5s would be taking 50 from this, and that would leave us with 33. And then a student might say, yeah, well, we can take 6 5s from that. And so you'd write down 6 up here like that, and you take away 30, and there's your remainder of 3. And again, this is developing the idea that division solves down, but records the answer on top. And of course, that answer is 1619. There's a total of 19 there with a remainder of 3/5. And we compare it to the standard algorithm by saying that if we know we did the standard algorithm with this, we would have gone like this. We would have taken away 1 and ended up with 4 and dropped the 8 and had 48. 5 goes into that 9 times. That's 45, and there's 3 left over, and it produces the same result. It's just that we took away groups of 5s all at once. Well, this started out by taking away single 5s, and it was really inefficient. So we do that a couple times, again, to develop that idea that division solves downward and records on top, and that you're always subtracting things away. This is actually kind of a good method here. Sometimes students can face like this, and I use the next step up. If it was 8 and a 97, we say, well, I don't know for sure, but I just use 10, because that gets me 80. And I can do 80, 17. I can take 2 more from that. That's 16. I've got 1 there, and I know that my answer is 12, with 1/8 as my remainder there. And this is called the expanded form of the division algorithm. So I've got another page to show that. We'll do a little more of those. Thanks for your patience. I'm trying to keep this video as speedy as I can. So say you got a number like 3 into 46. You ask the students again, what should you guess with if you're using the expanded form and you're not sure how this all works yet with long division? Well, they might say, well, I know 10 again. That's 30. And I would subtract downward and get 16, and then I know 5